So the other day I was making a cup of tea and I was thinking to myself, I wonder if I can predict what the temperature of the tea is going to be if I combine some really hot water with a little bit of milk. I like a little milk in my tea. And so I was thinking I could apply thermodynamics to figure that out. So I'm going to run a little experiment here to just see how close we get from our theoretical calculations and how closely they compare to an experiment. So to come over here and take a look, I've got a thermal mug here that's actually filled with 200 milliliters of hot water. So I have a little thermometer here, and I'm going to put that in just so we can get a quick temperature of the hot water. So it might be a little hard to see on the screen, so I'll read out what the temperature is. I'm getting about 70, let's see here. It's bouncing around a little bit, but it's 75 degrees to 74 degrees, somewhere in there. And then I have 50 milliliters of milk, and let's go ahead and get a temperature of that. Maybe you can see that better. So that one's at 9.2 degrees Celsius. So what I'm going to do is take that milk and combine it in with the hot water. I'm going to stir it up a bit. I'm going to put this lid on to try to reduce the amount of heat transfer. This actually has a hole in it, conveniently enough. I'll put the thermometer in there and just kind of keep track of the temperature. We'll let it come into equilibrium. It might take a little bit of time. So we're currently at about 62 degrees Celsius. It's holding pretty steady. I think we're going to, the final temperature there, it'll probably be about 60. So there it's 61.8. I think we've reached a thermal equilibrium there. Yeah, so I think we'll just call it 62 degrees for the equilibrium temperature. So what we'll do next is we'll do some calculations and see what we come out to for our predicted equilibrium temperature. Okay, so let's go ahead and analyze the teacup problem. So what we said is we had, I'm just going to draw this schematically. Let's say here is our milk. Let's call that, just so I don't have to keep writing the word milk, let's just call that liquid A, and then here's our water, and we'll call that liquid B, again, just so I don't have to write it out so much. In state 1, they're separate, and then in state 2, they're added together. So we'll just say A plus B added together. And we said from our measurements that the mass of A, actually it was the volume of A, the volume of the milk that we're dealing with was 50 milliliters. And the temperature initially was, what was it? It was 9.2 degrees Celsius. And then the volume of B, volume of the water, is 200 milliliters. And the temperature that we're starting off with initially was 75 degrees Celsius. And then at state 2, we know that we mix them together, so we know that the masses will sum together, so that the final mass will be Ma plus Mb, and the final temperature at state 2, so temperature of A plus B at state 2 is, we had said was, I think it was 62 degrees Celsius. Okay, so let me just put a subscript 1 there. So we're going to analyze this using the first law. And the reason I'm thinking the first law is because I'm interested in how the temperature is changing. I've got, my milk here, and that has some internal energy to it, corresponding to a temperature of 9.2 degrees Celsius. Same sort of thing with the water. It has some internal energy to it. And then when we mix them together, we're combining the internal energies. This reminds me of this makes me think of a first law kind of problem. So I'm going to draw a control volume. So here is initially what my control volume consists of, the milk and water separately, and then at the end, they're combined together. And I'm going to apply the first law here. So So we'll write it out. So the change in total energy of our system is equal to the heat added into the system minus the work done by the system. Now if I look at that for a moment, there is no heat transfer, I'm going to assume, because I've insulated the mug that I added the water and milk into. So I'm going to assume that the heat transfer is about 0. Also, there's no work because there's no boundary work, there's no piston here, there's no electrical work, there's no rotating shaft or anything like that. This is all what we call a passive system. And so that just means that the change in total energy is equal to 0. Now the change in total energy consists of a change in internal energy plus a change in kinetic energy plus a change in potential energy. And we know that the milk and the water, we're not changing the potential energy of those. We're not changing their kinetic energy. They're not flying around the room. So in the end, we have the change in internal energy of our system is equal to 0 in this process. Now the internal energy is going to be the internal energy after minus the internal energy before. That's the change in internal energy. And so the internal energy in state 2 will be the mass of the milk plus the mass of the water times the specific internal energy at the end. And initially, we have the milk and water separately, so we'll have the mass of the milk times its initial internal energy, and then we'll have the mass of the water times its specific internal energy initially. And so let's go ahead and combine a couple of things here. I'm going to combine the A items here. So, oh, by the way, one of the things I should mention is the specific internal energy at state 2 here. It's going to be the same specific internal energy for the milk and the water because they're in thermal equilibrium. So they're just in equilibrium with one another, so they'll have the same final specific internal energy. So let me combine the mass A terms, and then I'll do the same with the mass B terms. The reason I'm going to do that is because what I'm going to do next is I'm going to just rewrite the change in specific internal energy. I'm going to assume that the milk and water are incompressible. And in addition, I'm going to say that they have a constant specific heat, and the specific heat is the same between them. So let me write that. Are incompressible and have a constant specific heat, and the specific heat of the milk is going to be the same as the specific heat of the water. So I'll just call it C. Let me address all of those assumptions. So milk and water being incompressible, that's a very good assumption. Milk and water are both liquids. Liquids are often treated as being incompressible. Their specific volume doesn't change much unless you have a very large change in pressure, for example. So that's a pretty good assumption. As far as constant specific heats, I guess I forgot the word heat there. That's also a pretty decent assumption, constant specific heats. Now remember, in general, for an incompressible substance, the specific heat is generally a function of temperature, but our temperature changes here are not that drastic. So we're going from almost 10 degrees Celsius to 62, so that's about a 50 degree temperature change. Here it's 75 degrees to 62, so about a 10 degree temperature change. We're not talking about hundreds and hundreds of degrees temperature change. So over that small range of temperatures, the specific heat remains more or less constant. So that's a pretty good assumption. Now, the final assumption I made here is that the specific heat of the milk and the specific heat of the water, I'm assuming, are the same. That's also pretty good because milk is something like 90% water. And if you're dealing with skim milk, like I actually did in the video, it's even closer to being water. So since milk is mostly water, it's going to have very similar properties, so I think that's also a very reasonable assumption. Now, using those assumptions, what happens is the change in specific internal energy becomes the specific heat times the change in temperature. So we can write that for both of these. Okay, so I can only do that step because of these assumptions. I've put those in right there. Now, if you look at this, there's going to be a C here and a C here, so I can divide through by those without any problem. And so then I'm left with MA times T2 minus TA1 plus MB times T2 minus TA1 equals 0. What I'm going to do now is just do some rearranging, just some algebra to solve for T2. So this will be MA plus MB times T2 minus MA TA1 minus MB. Oops, this one should have been this should have been a B here, sorry, times TB1. And then I'll just do a little more algebra. What I've done is I brought these two terms over to the right-hand side, so I'm bringing them over to this side, and then just dividing through by the mass A plus the mass B. And then that gives me a way to solve for the final temperature. If you look at that expression, you'll see that what it is actually a mass-weighted contribution of the temperatures of each one. So here's the initial temperature of the milk. Here's the initial temperature of the water. So what I'm doing is I'm taking the initial temperature of the milk and I'm multiplying it by the fraction of the total mass, that's the milk. And then here's the initial temperature of the water multiplied by the fraction of total mass that was water, or that is water. So in our problem, our experiment, we actually had the volume of the milk and the volume of the water. We can find the masses from those because we know that if we're going to treat it as being like water, the mass of the milk would be the density of water times the volume of the water. And we can do the same thing for the actual water. And we know that the density of water is about 1,000 kilograms per cubic meter. That's a very good approximation. Then we multiply by the volume of the milk. It was 50 milliliters. And then there's a unit conversion here. So getting this in terms of cubic meters, what we have is 1 cubic meter is 1,000 liters. And then actually I've got milliliters here, so I put an extra 1,000 in there. Let's see. So 1,000 liters and then 1, 2, 3 milliliters. And you can do the same thing here for the water. Same unit conversion. And what you'll get is the mass of the milk comes out to be 5.00 times 10 to the minus 2 kilograms. The mass of the water is 2 times 10 to the minus 1 kilograms. And then I said, we have the temperature of the milk initially was 9.2 degrees C, and the temperature of the water initially was 75 degrees C. And when we plug those numbers in, what we'll get is the final temperature comes out to be 61.8 degrees C. Now, if you take a look at the video, we found that the final temperature experimentally was about 62 degrees C. So you can see our prediction is very good. And in fact, I think somewhere in the video we found that the temperature was actually, we read it off, it was 61.8, and then it was somewhere between 62 and 61.8. So our prediction is really quite good. So I guess we can conclude that thermodynamics works. We did a good job predicting our final T temperature. All right, we'll end it there.